Hello, this is Mahmoud Banasi. Today I'm going to present you Deep Q learning, a reinforcement learning technique that uses neural network. So in order to understand this, we need to understand what is reinforcement learning, and also we need to understand how we use neural network in that. Reinforcement learning is an area of machine learning that focuses on how an agent acts in an environment to maximize some given rewards. So we have an agent, we have an environment, and we have the interaction between the agent and environment. This interaction leads to a reward. This reward is used to update to train the agent. Similar to a human who tries to achieve a certain goal without supervision. So the main component here is there is no supervision, only rewards that we are getting from the environment. An example for this is video gaming, control a helicopter, robotics, and the most famous example is AlphaGo, when reinforcement learning agent were able to beat world champion in Go game. So reinforcement learning uses Markov decision process. Markov decision process provides a way to formalize sequential decision making process. What does this mean? It means that the agent would read the state of the environment, state S at time t, and then will take an action at time t, A at time t, and then will apply this action or forward this action to the environment, and the environment will do some stuff, generate the new state or move to the new state S at time t plus 1, and at the same time also generates a reward R at t plus 1, and this reward will be used to update to train the agent, as we can see in here in the plot. So considering this, the main task of the real agent is to define the policy. So the agent tries to define this policy. This policy could be defined as a deterministic policy or a probabilistic policy. Deterministic policy, like if we have a simple function that maps between a state S and an action A, or a probabilistic policy when we have a probability function that gives us a probability of getting an action A, providing that or giving a state S. So this would be a probabilistic policy. The environment provides a reward that is generated as an output of applying an action A given state S. This reward actually is used to calculate the Q value on the state value. So the Q value is the value of taking an action A at state S. The state value is basically the value of being at the state S. Q value and the state value are used to guide the RL agent or guide the training of RL agent. So this takes us to a simple example to illustrate the main idea. So for example, in the 2D grid world, when we have a two-dimensional grid, we have two goals marked with gray, and any state in between is not the optimal state, so we have given it a reward -1 to indicate that this is not a good state to be in this system. So for example, if we started at a random state, let me use a pointer here. If we started at random state here, and then we take a decision to move right, and after moving right, we found ourselves that in a state that has a value of -1. Thus, intuitively, this means that the state that we had before should have a worse value than the current state. Another meaning, the state that we had before should consider in its value the value of the transition to this current state. So in order to do this, what I'm doing here is basically updating the state value of the previous state by adding the state value of the current state. As you can see here, this becomes -2 instead of -1. Doing the same step again, for example, take an action to move right, then we moved right, then we found a state that has -1. So in this case, we update the state of the previous state and becomes -1 plus -1, which means -2, and the state before that, which is -2 plus the -1 that we got from here, so this becomes -3. And repeating this step over and over and over again up to the end, we will find this policy or a state value table that gives us the policy of our system. As we can see here, this state value gives us enough information for a policy. For example, if we start at a random state, let's say this state that has -20, and if we started here, we can see that if we move to the right, to the left, or to the bottom, this would be the highest reward that we can get here, as the reward in this case would be positive 2. And if we move at any other state, we will have a worse reward worse than that. If we move from this state to either to the right and up, down again, we will get also the highest possible reward. And then from this state, we need to move right in order to get to our goal. And this summarizes the main process of reinforcement learning. So one thing that we've noticed in this example, as initial training phase, we don't have enough information in our policy in order to take decision. So in this case, we randomly select the action. This process has a name, actually. It's called exploitation versus exploration, meaning that at the beginning of the training, we don't have enough information about the network, about the policy, so we basically exploring the environment. By exploring means that we select actions randomly and with high probability, with probability of 1. And as the training goes on and on, we reduce this exploration factor and we start exploiting the environment, exploiting the policy to generate actions. In this case, we can see the exploration factor is reducing and the exploitation is increasing up to the end until the end of training, and now we can 100% exploit the policy. This method called epsilon greedy strategy, when we reduce the exploration and increase the exploitation gradually with the training steps or training episode. Bellman equation. Bellman equation used to define how reward is used to update the state. Or basically, this is the process that we have done before when we have when in the 2D grid, when we move to a state S prime and we had a value for the state S, and in order to update this, we need to consider the reward, the transition from a state to another state, and the value of the new state. So if we consider that, for example, if we take a trajectory that we moved right, down, this would give us the full trajectory. And in this case, we need to consider the whole trajectory in order to update the state, the value of the state S. So this is what we have here. If we moved to a state and then we move to another state and then the reward of the third state and then the reward up to the n states. But we can see also there is a factor gamma that reduces the value of the reward for the farthest future. So the value that we get in the far future doesn't have the same effect like the value that we get from the near future. So this gives us some kind of appreciation for the rewards in the near future and reduces the effect of the reward in the far future. This function is basically could be summarized to something like this, which is they are exactly identical, and this is basically what exactly we have used in our previous example, except that gamma was 1 in our case. So the transition, the reward that we got from moving to a next state, which is in our case was -1, plus the value of the state that we had, which was -1, and this gives us -2, as we saw in our example. So again, the discounted factor gamma is a value between 0 and 1. Usually it's 0.099 or 0.0999. The same also could be applied to the Q value, similar to the state value. So the Q value, the only difference is the Q value is the value of taking an action A given a state S. So we can apply exactly the same concept here, and this is what we got here, which is the expectation of R at time t+1 plus gamma of the Q value of S t+1 with the next action of this, the next best action at state t+1. As we will see later, this would be the maximum Q value. So finding the optimal policy. For any Markov decision process, there is always an optimal policy, and this policy must achieve the optimal state value function and the optimal Q value function, as we saw here. So we can formulate this in mathematical equation like this. So the optimal policy pi star given S and A for state S and A would give us 1 if and only if the selecting action A given at state S with the optimal Q value function would give us the maximum value. So this would give us 1. If it doesn't give us the maximum value, if S and A is not the argmax, then we are not going to select this action, and this will give us a probability of 0, or the selection of 0. To achieve the optimal policy, we need to get the optimal Q value, as we can see here. So this basically are two examples this is the examples that we have discussed before, and the same example could be approximated in a policy way. So, as we can see here, this is the policy moving down or left, and instead of having all numbers and doing the calculation over and over again, which is a simpler way to represent the same table. Limitation of Q-learning. This is the main concept. Why are we interested in neural network here? So the main concept and the main problem in reinforcement learning is limitation in space, in scale, in the environment size. So it performs very well with a small scale environment, limited number of states, limited number of actions. However, it doesn't scale very well with large environment, like for example in a video game or robotic control or something like that, or self-driving car, when you have a bunch of inputs from the video cameras and sensors in the car and traffic signal. All this information are huge to be simply presented in a table. So in order to overcome this, we use neural network, because neural network basically performs very well as a function approximation. What we need at the end of the day is an approximation for a state action mapping. So we need a function that approximates the state and gives us an action based on the policy that we have in the network. So considering this, we can approximate our system using a neural network. The state representation will be used as an input for the neural network. The actions will be the output of the neural network. As we saw in our simple example, the actions are basically up, down, left, right. We have 4 actions, simple 4 actions here. And the training will be performed similar to a supervised learning, using the same backpropagation, gradient descent, or the same concept of neural network in general. So we can see 2 main challenges here. The first one is data generated from the environment are sequential and tightly correlated, because we start with a state and we apply an action, and then we get a new state, and we apply this new state into the neural network, and we get another action, and then so it's sequential. This might create a correlation between the data and might lead to a local optima. In order to avoid this, we use a replay buffer, which basically we do the trajectory for a state action, and then we save those to a buffer, and then from this memory buffer or replay buffer, we randomly select the state, action, reward, and next state, and we apply the training based on those randomly selected values or randomly selected samples. This will remove this correlation and will make the system stable. The other problem is the oscillation in the reward calculation using DQN network. So the main issue here is the neural network, the reinforcement learning itself is not stable, and the values might oscillate too much. In order to avoid this, we create 2 copies of the neural network, 1 copy for the action and another copy for the training or the policy itself. And the action will be used to generate the action, apply it to the network, and then the training will not update the same network, but it will update another network, which is the policy network, and this policy network will be frequently copied to the action network in order to make the system more stable, in order to avoid this oscillation. So in general, how it works, so we basically initialize everything. We start with initial state, and we select an action, execute selected action, observe the reward, and save this information to a replay buffer. Up to here, we interacted with the network, and then now the training part. The training part, we sample from the replay buffer, if there is enough sample for sure in the training buffer, or the replay buffer, I'm sorry, and we process this and pass this batch into the neural network, calculate the loss, and this is the equation for the loss, and we'll come later to explain this loss function. And then we update the weight of the network, and then move the next state to the state, and repeat the same process until we get to a terminal state. So let's visualize this a little bit. So this is the loss function. As you can see here, the loss function is basically the expectation of the loss function from the policy network and the expectation that we got actually from the experience from applying the reward on the network. So we apply within the loop, we start with a state, go further to the next state, get an action, go to the next state, apply the next state, get an action, apply the next state, and then go forward until we get to an n number of states, or we get to a terminal state, and then this would be used to guide our training, because our objective is to have the policy networks that we get this information from is identical to what we get from the environment. So taking this in consideration, we start with an action network, we apply the state, a randomly selected state, and we get an action. This action gets applied into the network, and this applied to the environment, which generate a reward. And this reward, as you can see, this is the first term in the equation here. And based on this reward, based on the transition of the system of the environment, we generate a new state S prime. This S prime also is taken and applied to the policy network, and this policy network will generate Q value for the maximum Q value for the next action on the next state, and this is basically also, again, this is the maximum value that we have gotten here. The only missing part is this expectation of the sum of the reward, and this basically, after repeating the same process over and over, going through the steps, we will get this reward and the sum of it. We also need to save this information that we got from the state, action, next state, reward into our replay buffer for the training purpose in the next epochs. And this would give us everything that we need for the calculation of the sum of the reward, which gives us the calculation of the loss. And now we can apply the normal backpropagation and stochastic gradient descent, or any optimizer in the neural networks that we would like to use in order to train our network to get this policy for the agent. And this summarizes the DeepQN algorithm. As we can see here, as in the conclusion, the DQN was developed in 2015. It combines the reinforcement learning and deep neural network. It was able to solve a wide range of Atari games. It also has successful deployment in helicopter control and robotic control. Still, some challenges exist, and new approaches try to address them. For example, deep deterministic policy gradient is proposed to address the continuous action space, and we also have the twin delayed DDPG, which is also proposed to better enhance DDPG, and advantage actor critic, which is also proposed to address the stability of the system. Those are just examples. There's other algorithms out there that proposed using the same concept of deep reinforcement learning. Hopefully this was informative for you, and thanks. And now we are ready to take any questions. Thanks. Have a good day. Bye.